The topic this video is going to cover is finding the volume of a solid created with cross-sections that are known. To get a basic understanding of this idea in context of a problem that you'll be given, we'll be working with an example problem. This problem is asking you to find the volume of a solid with a base that's the area enclosed by the functions f of x is equal to x, the x-axis, and x is equal to 5. Cross-sections perpendicular to the x-axis are squares, and it wants you to find the volume of a solid created with the given criteria. Now, if you've never worked with this kind of problem before, it can be a bit overwhelming, but I'm going to try to represent this geometrically with the ultimate goal of representing it using calculus and algebra. So as you can see here, I've represented the function f of x is equal to x with this blue line, x is equal to 5 with this red line, and the x-axis and y-axis here. Now, this green area is the area enclosed by f of x, x is equal to 5, and the x-axis. So shaded in green there is the base of the solid that's created. Now, here, once again, we have our f of x is equal to x, x is equal to 5, and the x-axis. And this green line here is showing the base of a cross-section arbitrarily located at some x value from where f of x crosses the x-axis, which is at 0, and at x is equal to 5. So it's just bounded here by those x values. And this is an arbitrary base of a cross-section located arbitrarily between those bounds. So, we know that cross-sections are squares. So, your f of x, the distance from f of x to the x-axis is this green line here. Now, that distance, by the very nature of a square, we know that all sides are equal. So, if the cross-section is a square, then the distance from f of x to the x-axis is also the height of the cross-section as well as the width. So, essentially that's the distance from f of x is equal to x to the x-axis squared is the area of this. Now, if you wanted to find the volume of the whole solid, you would sum up the areas of every single square from 0 to 5. And that would be the volume of the solid. So, to represent that using algebra, we have here function f of x is equal to x. That is the length of the side, as I've stated previously. So, we know the equation for the area of a square is the area is equal to one side squared. So, as we know, the side of the square is the distance from f of x to the x-axis. And since we know that f of x is equal to x, we can just say that the distance from x-axis to the f of x is x, simply. So, x is the length of the side of the square, and thusly we can say that the area of this square, any arbitrary square cross-section on this solid, it can be represented by x squared. And if we wanted to find the volume of the whole solid, we would take the integral between the bounds of every square. So in context of this problem, we can represent that as the volume of the solid is the integral from 0 to 5, those are the bounds, is x squared. So that's just the area of every square. So that's quite simple, but we can also use this basic idea to also find the volume of a solid with a base that is enclosed between two different functions, not just one function and an axis, which in itself is just x is equal to 0 or y equals 0 anyway. So, we're going to look at two functions, distinct functions, bounding the base of a solid. So, for an example problem, The base of the solid is the area enclosed by the functions f of x is cosine x, g of x is sine x, and the y-axis. Cross sections perpendicular to the x-axis are semicircles, different from our squares in the previous problem, and it wants you to find the volume of the solid, once again, given with these criteria. So, here, geometrically represented the base of the solid. It's enclosed by this yellow function, sine x. That's g of x. Your f of x, which is cosine x, that's your blue line here. And the y-axis. So this here area is the base of the solid. And once again, green line representing across the base of the cross section, or the diameter of the semicircle that you'll be working, any semicircle you'll be working with, that's arbitrarily located between x is equal to 0 and where sine x and cosine x intersect. So this is the bound. So here you can see that's the diameter of the semicircle, and we have semicircle drawn here. That is an arbitrary cross section drawn just to represent what a cross section would look like in this problem. And if you wanted to find the volume of the whole solid, you would just take the integral of your diameter here, and we'll represent that algebraically. As you can see, you have your f of x cosine x, g of x sine of x, and the diameter of the semicircle is your f of x minus your g of x. That's just finding the distance between them. And the radius is your diameter over 2, we know that. So, to find the area of the semicircle, we can represent that as 1/2 pi r squared, is the area of any semicircle. And if we know our radius is our f of x minus g of x, that's cosine x minus sine x, over 2, that's your radius. That's in context of this problem, so plug that in for your radius. That's the area of any cross-section, any arbitrary cross-section between 0 and pi of 4, where sine x and cosine x meet. So if you want to find the volume of the whole solid, once again, you take the integral of the area of that area here. So, once again, in context of this problem, the volume of the solid is pi over 8 times the integral from 0 to pi over 4, where sine x and cosine x meet, at x equals pi over 4, of cosine x minus sine x squared. Okay. Now, the previous two problems we've been working with cross sections that are perpendicular to the x-axis, but we can also work with them when they're perpendicular to the y-axis. But don't worry, it's just as simple, and you won't face any new obstacles with this, really. So in this example problem, the area of the base of the curve is enclosed by the functions y is equal to x, y is equal to 4, and the y-axis. The problem is asking you to find the volume of the solid generated with cross sections. Cross sections are squares perpendicular to the y-axis. So, once again, I'm representing this geometrically. You can see the function y is equal to x in orange here, and y is equal to 4 here in the blue line. And this red line here, once again, is representing an arbitrary base of the cross section located between your bounds. And in context of this problem, since we're working with cross sections perpendicular to the y-axis, like this, we'll be working with bounds in terms of your y values, which is y is equal to 0, where our orange function here passes the y-axis, and y is equal to 4, where the blue one crosses the y-axis. That's a little bit different from our previous problems where we were bounding it in terms of your x values. So, as we've represented with our base of the cross section here, in the red line, we have the full cross section drawn out here. This is just the base of it. And the distance from your orange function, y is equal to x, to the y-axis, is you can represent that essentially as y minus 0, because your y value here, your x value here, is 0. So that's the distance from here to here. So you know that the sides of the cross section is the distance is your y value, y minus 0. So the area of the cross section, because it's a square, is this distance y squared. And the volume of the solid, we would take the integral of the area of each cross section, these squares, between the bounds 0 and 4. Now, if we wanted to represent that algebraically, we can say the volume is the integral from 0 to 4 of your y squared, and that's you can represent the area of any cross section. And then to find the volume, you find the antiderivative by raising the power, dividing by that power between the bounds 0 and 4. Then simplify that out, work that out, you get 64 over 3 minus 0, which ends up being 64 over 3. So, thank you very much. This production was brought to you by Alex Person, Doa Palmaclar, and Brant Palmer.